maybe it's time to get started. So it's our great pleasure to have Massimo Fornasier today as our speaker. Massimo received his PhD from the University of Padua and then went on a number of different venues. He was in Austria at NUHAC as a postdoc, funded by Marie Curie, and then also had some other stations in Germany before before becoming a research associate at the Austrian Academy of Science, at RICAM in Linz, where he was for a number of years and one of the leaders of the group of analysis of partial differential equations. And from there, he moved to Technical University of Munich, where he has been since 2011 a full professor in applied numerical analysis. So he received a number of awards, including the Austrian Stark Prize and the ERC starting grant. So it's a great pleasure, Massimo, to have you here and to talk to us about consensus-based optimization on this field.
So thank you very much, Felix and Mark, and the other organizers of this One World seminar. So tonight here in Europe, of course, I would like to introduce you to some new results that we provided about global optimization in high dimension. And in particular, this talk would be about global optimization on the high dimensional sphere. And I would like to start with some few words of motivation. So as all we know, machine learning is about essentially parametric nonlinear functions or algorithms, and the parameters are optimized towards several tasks like feature selection, dimensionality reduction, clustering, classification, regression, and so on. The typical nonlinearity of the function or the non-convexity of the data misfit make the training of such algorithms or such functions a non-convex optimization. Moreover, the large amount of parameters that are characterizing these algorithms or functions make the optimization high dimensional and in some cases quite hard. So first order methods such as gradient descent are preferred because of speed, scalability, and because they are considered generically able to escape the trap of critical points like saddle points. And in some scenarios, it's possible to prove that actually they may even be able to converge to global minimizers. Nevertheless, in general, gradient descent, they may have some drawbacks, especially when the function itself is not differentiable or is not possible to access the gradient of the function itself, or it is too expensive to compute it. There are situations where there are some catastrophic behavior of gradient descent, like the explosion or the vanishing of gradients, as it happens in the training of very deep feed-forward neural networks. And in general, despite the fact that there are some good features of gradient descent to escape critical points, there is no guarantee that you may converge to a global minimizer. So this is a bit about machine learning and how come that high dimensional optimization is so important. But say long before the current trends in machine learning, non-convex optimization had been considered for the optimal design of any sort of process. And so this is not a new task, especially the high dimensional problem of optimization is not at all a new type of challenge. And in the past, there has been many algorithms that have been considered to provide a global optimization. And these algorithms are often somehow made of multiple optimizing agents that orchestrate an interaction between themselves, where local improvements procedures and global strategy are mixed, as well as these agents are combining random and deterministic decisions. So gradient descent or stochastic gradient descent is all about one optimizing agent that individually is moving along the profile of the function that it wants to optimize. But that's all that that agent can do. There is a sort of zoo of different kind of algorithms, starting with the simplest heuristics back to the 60s, but then there's been many other algorithms that came up with these concepts. And among the most popular, maybe there are genetic algorithms very much used in practice, as well as particle swarm optimization. So these methods are towards, so when you challenge them with respect to certain benchmarks, they show tremendous empirical success. But for most of them, there is in general, lack of guarantees of convergence of global minimizers, despite the fact that they do perform so great. And this is mostly because of the randomness and certain kind of somehow mechanism that often are used, like memory mechanism, trying to remember what was the best performance of a certain agent along its trajectory and all this kind of stuff. So trying to analyze these algorithms is not that easy. But recent work done by Pinot and others, and later by Jose Antonio Carrillo, Pinot and others, introduced a new version of this kind of meta-heuristics called consensus-based optimization, which is about instantaneous. And this is very important because I spoke about memory, somehow memory mechanisms that are about the past. But here, somehow the stochastic behavior is an instantaneous one, so that we can better handle it in the sense of how that propagate dependencies. And deterministic decisions, in order to establish consensus among agents, optimizing agents that we may simply call particles here, on the occasion of the global minimizers. So this is more or less what they do. They try to have an idea, they try to have a sort of consensus on a possible proxy for the global minimizers. They try to move around it, and at the same time, they explore a random limit environment. I will be more precise in a moment. The evolution, thanks to this instantaneous stochastic somehow mechanism, can be interpreted as a system of stochastic differential equations. So in a certain sense, the algorithm is interpreted as a discrete time approximation to a system of stochastic differential equations. And the large particle limit, which means when we use a larger and larger number of agents, is approximated by the solution of a deterministic partial differential equation of mean field type. It's like a sort of Fokker-Planck type of equation. Interestingly enough, once you have this deterministic partial differential equation, you can use relatively classical deterministic type of tools of analysis that allows you to show that the solution of the partial differential equation does converge to a Dirac delta on a global minimizer. So this is a bit a chain of reasoning of a possible proof of how these methods do work. There is some theoretical gaps though, and in particular the fact that the mean field limit or the large particle limit is really established. So the problem here is that we expect that the large particle limit can be approximated by a deterministic partial differential equation, but on the Euclidean space, there is a lack of compactness by the dynamics. At least it has not been in the work by Carrillo and others. They have not been able to establish enough compactness to really prove such a limit. So here you can see an example of a function that have many local minimizers, one global minimizer quite far away from where the agents are. And the agent starts very far away, they move randomly, and at some point, one particle senses the presence of a better location of the function, and by doing so, it's communicating somehow this information to the other particles, and everybody eventually agrees with this other particle, and they converge to the global minimizer. So as you can see, this is a function that won't ever be easily minimized by gradient descent, especially in high dimension. Some randomly finding this this position where there is a global minimizer would be nearly somehow infeasible task. And so in a certain sense, this is a remarkable type of behavior. So motivated by the fact that the theory still was lacking this particular mean field limit due to lack of compactness, and because of the many applications of the specific type of optimization, we have been considering optimizing function on a compact manifold. So in particular on the sphere. So we are considering a compact manifold, and in particular a sphere, because then somehow we can get compactness by domain rather than compactness by the dynamics. And so in a certain sense, we can expect that that particular gap can be closed, and we can really have a complete proof of convergence, which I'm going to show you in a moment. However, changing the domain obviously change completely the dynamics of the particles, and one have to come up with the right formulation of such a particle system on the sphere. And the particle system, as I said, can be interpreted as a time discretization of a SD system that describe the motion of n interacting particles or optimizing agents. And the SDE looks like that. Okay, it's very complicated, but now I'm going through all these different pieces of this equation. So this is the equation of the particle I. And in this equation, you can see that there is a projector, orthoprojector appearing here. And this projector is nothing else than the projection onto the tangent plane or the tangent space to the sphere at the position VI. And there is another object that appears, which is rho n. And rho n is the empirical measure of the particles. So in a certain sense, it's a train of Dirac deltas supported on the position of the particles. By using this empirical measure, we are building a possible proxy for a global minimizer. And this proxy, we call it V alpha, that appears here and appears also in the equation. V alpha is morally a weighted center of mass of the particle, of the particles, where the mass of a particle is, in a certain sense, exponentially inverse proportional to the function that we want to minimize. So those functions that have a small value of this function, those particles that have a small value of this function are those particles that have larger mass, and the particles that are having instead a very large value of this function, so they are very far away from the target, they have a smaller mass. And so, in a certain sense, this is a convex combination of these particles, but the weight, how we weight that depends on the function that we want to minimize. The parameter alpha, it's an important parameter that, if you want, we call temperature parameter, so that we will remember it later. And it is one of the tuning parameters of this algorithm. So what we do, we first move the particles with a speed, with a velocity that is, in a certain sense, bringing them in the towards the target global minimizer. What is particularly intriguing is that, being a convex combination of particles on the sphere, this target at the beginning is actually inside the sphere. So it's not lying on the surface of the sphere, but it's inside. That's why we have to project it on the tangent space. The second term, instead, is a projected Brownian motion. So this is a Brownian motion, say, in the embedded space, Euclidean space RD, and then we project it on the tangent plane. And the intensity of it depends on whether the particle already agrees on the fact that it's very close to a global minimizer. If that is not the case, and this distance is pretty large, then the particle will continue to explore the environment pretty wildly. So it moved very fast because of this Brownian motion. The last term is a technical term. So it is about Ito calculus that allows you to prove that, despite the Brownian motion, and despite the projection of the Brownian motion on the tangent plane, really the particles are keeping moving on the sphere. So this is a sort of correction term that allows you always to stay on the sphere. Okay, this is the dynamics that, as I said, you can discretize in time. And if you discretize in time, you choose your favorite time discretization, maybe an explicit scheme, like an Euler type of scheme. In the stochastic business, the Euler schemes are called Euler-Maruyama type of schemes. And then afterwards, you may project back on the sphere. But you can use any type of discretization, implicit discretization, and or discretization that are more geometrical, that they are taking into account that you want to stay on the sphere. And so depending on the kind of discretization you have one more optimization algorithm that comes into the game. So how does it work on the sphere? So here we can see a function that is one of the benchmark test function in optimization called Ackley function. And the Ackley function is characterized by multiple local minimizers and one distinct global minimizer that is clearly somehow having a value of the function significantly smaller than the rest, okay? And nevertheless, somehow this kind of particle method is ignoring completely the local minimizers and is able to converge pretty nicely to the global solution. This is not only happening with such a simple function, you can do it with nastier function where the difference between the global minimizers and the local minimizers is not pronounced. And so in a certain sense, it's not that simple really to be able to find which minimizer is really the global one. But nevertheless, you can do it. And even more, somehow this method can be generalized to other type of compact manifolds. So far, we have formulations for compact hypersurfaces, and we are working now to try to generalize it to a little bit more general compact manifolds. So here we see a sort of Ackley function on the torus that one can optimize. Okay, so I hope that up to this point everything is kind of clear. I don't know whether there are questions about the mechanics of the topic, or somehow I can move from here.
I was wondering, when you're projecting onto the tangent plane, as part of your description, which tangent plane are you projecting onto specifically, especially for the sphere?
What do you mean? So this is the the kind of explicit formula, let's say, of the projector. I don't understand what you mean. Which tangent plane? Which tangent? Well, it is a tangent hyperplane, I would say.
Yeah. Okay. I meant tangent to what point, I guess, was.
Okay. So the point where the particle is sitting.
Yeah. Okay. That makes sense.
So
you're just taking a random walk in a specific direction, sort of toward, based on this empirical density that the other points are informing, as they also take
exactly. So the system is coupled through this this quantity that is summing up basically it's summing up the particles. So it is the place where somehow you need to know where they are, right?
Got it.
What I have to mention is that there is no gradient information about the function used ever. So it is a zero ordered scheme. So you don't use first or second order information, right?
Okay. Yeah. Thanks. That makes sense.
All right. So this is a bit the description. Now, exclusively for the proof and the technical tools that we're using that are basically based on calculus. First of all, stochastic calculus, Ito calculus, and then also somehow classical calculus based on this PDE. We need a little bit of regularity of the function E, but this is, if you want, due to the necessity of having a proof. You can use the algorithm even if E is not that smooth, and the results are still very good. But in that case, we don't have a proof. The other important property that needs to be fulfilled is what we call the inverse continuity property, or stability property, or whatever you want to call it, which means that the level set of the function characterize also the distance from a global minimizer. So E underscore here is indicating the infimum of E. And so here we are checking how far we are from the infimum, but this is controlling also the distance from a minimizer. Okay, so this is an important property that that otherwise won't allow you to say that you can converge really to a global minimizer. Although if this property does not fail, the algorithm would converge a minimum of the function E, although you cannot say that you converge to a minimizer. Okay, so that's something that one can say. So the main theorem is the following. For all epsilons, and I will explain why this epsilon come into the game later, and somehow one can assume that the initial datum, so the way we generate the particles at the beginning, and the parameters of the algorithm are well prepared. So in the algorithm here, there are two parameters. There is a parameter lambda that is appearing in the equation here. And there is a parameter sigma, and these need to be well prepared, as well as the parameter alpha that needs to be sufficiently large. And then there is a time horizon that is defined, and then one can prove that the average of the particles computed by the algorithm. So here we are really considering the time discrete version of the system, and we average the particle. Then the average of the particle will be close to the global minimizer in the square distance on expectation from the generation of the particles at the very beginning. And this error is bounded by three different quantities. The first is the discretization step to the order of the method that you use to discretize the SD system. The second is is scaling with respect to the number of particles. So the scaling is, by the way, with an exponential that is not affected by the curse of dimensionality. It's not like -2 divided by d, but it's like n to the 1 minus 1. And then there is this epsilon parameter that we fixed at the very beginning that I will explain to you how come it comes into the game like that. So this is the kind of result that you have. So you are guaranteed in this sense to converge to a global minimizer. Now, the well-posedness, so the steps of this theorem are the following. First of all, you want to establish the well-posedness of the multi-particle SD system, so to say that there is a unique solution. Then you introduce a monoparticle, so one process that is basically made of one particle that has the same equation as before, except for the fact that we don't compute the weighted center of mass according to the empirical measure of a multi-particle system, but we do it by computing it on the basis of the law of the monoparticle system. So this is a one equation only, where somehow here it's the law of the process appears into the game. Then we can show that this law of this monoparticle system actually is the solution of a certain Fokker-Planck equation on the sphere, where somehow the differential operators here are the ones that are defined by tangential projection, and in particular this one corresponds to the Laplace-Beltrami operator. Okay, and so now we have a deterministic PDE. So this is a completely a PDE that has no stochastic terms. And one more thing is that we can prove that the empirical measure of the multi-particle system converge to the law that we described here of this monoparticle system in the Wasserstein distance squared, an expected value, and this convergence goes like n to the -1. So this is exactly the place that it's difficult to prove, or so far we don't have a proof in the Euclidean space, and it can be done because of the compactness of the sphere. So this is one place where somehow the compactness play a significant role. Okay, so once we have this, we need a little bit more regularity of solutions that I will mention again. So we need that somehow we generate the particles with a density. So we need to start with some, not really just a probability measure, but we need also some density. And then it's possible to prove by playing with this equation that the expected value of this law at a relatively large time t star is going to be close to a global minimizer up to a certain epsilon. Now, the last step is basically a bunch of triangle-like inequalities, where, in a certain sense, we show that the expected particle is very close to any particle solving the stochastic differential equation system, and at the time t star. So, and then the empirical measure of the multi-particle system is closed to the solution of the PDE, and the expected value of the solution of the PDE is close to the global minimizer. And if you keep track of all these errors, that's exactly what you can get as a bound for the error. Now I would like to show you very quickly how these steps of the proof are done from a slightly more technical point of view. So the first fact is that we need to prove the well-posedness of the system of the SDEs, and as well as this monoparticle dynamics. And the way we do it is by trying to prove that SDE has solution in RD. And so we extend the projection operator and this other term that appears in the equation that was V divided by V squared. We extend these two quantities from the sphere outside the sphere in a smooth way. And at the same time, we are extending the function defined on the sphere outside the sphere in such a way that the extension is smooth smooth enough. And so all of a sudden, we can write the system as a system completely defined in RD. And the next step is basically to prove that this system has solutions, but these solutions necessarily keep staying on the sphere by construction of the dynamics. And so all of a sudden, the existence and uniqueness of solution in RD will be existence and uniqueness of solution on the sphere. So the way you get existence and uniqueness of solution is by showing that all the relevant terms have at least linear growth and they are Lipschitz. And so first of all, this is a typical thing in a sort of Cauchy-Lipschitz theory for stochastic differential equations. And the first thing is to establish the Lipschitz properties of this fundamental quantity that is the weighted center of mass. But once you have that, we can use somehow the fact that the coefficients are Lipschitz and use relatively standard resulting SDE that establish the well-posedness of it. And then, as I mentioned, by Ito formula, one tries to differentiate the process squared and show that the norm is keeping constant. And so if you start from the sphere, so which means that you start from norm 1 particles, you will stay on the sphere because the norm 1 will be preserved. And so you have well-posedness of the SDE. Similarly, you proceed for the well-posedness of the monoparticle system. And the only problem here is that here you have the law of the system. And the way you prove it is by saying that the equation has a solution if we include an arbitrary field here that is not the mean value particle, that the alpha that we have in the equation. So for any CT here, instead of V alpha, this system will have a solution because of the Lipschitz property of the coefficients. But then one has to try to create a fixed point argument where somehow one used the law of the system to define the law of the particle to define now the next type of field, and you try to prove that somehow there is a Schauder fixed point theorem applicable in this context. Okay, that's the way you prove well-posedness of the SDEs, and then by testing the process with respect to a smooth function and using Ito calculus, and then taking expectations on both sides, where the expectation with respect to the law, then we obtain actually a PDE in RD, completely defined in RD, and in a certain sense, this PDE it's about a law that is supported on the sphere. So instead of testing it on arbitrary smooth function in RD, one could test this equation for test functions that are actually normal extension of test functions on the sphere. So we take smooth functions on the sphere that are extended to be smooth outside of the sphere. And by doing this, we can show that the equations, whenever we test it on such functions, it collapses in a certain sense on a PDE written here in weak form with respect to stochastic differential operators defined on the sphere. So this is a construction that clearly says that starting with the monoparticle dynamics, one can construct a measure that is a weak solution of the PDE, and the uniqueness of this solution follows from the uniqueness of the process. And so we can establish also that the law of the process is actually a solution of the PDE, and it is unique. And then, as I said, the last step is proving that taking multiple monoparticles and taking the multiple particle system, it's morally doing the same thing as soon as the number of particles is becoming large. Okay, so there is this inequality that one has to prove, but this is provable exclusively thanks to the compactness of the sphere or the compactness of the manifold that we are considering. Okay, so I'm not getting into the details. It's just basically this is the inequality. So showing this inequality is crucial, but this inequality can be shown easily when we are on a compact manifold. It won't be that easy to prove it on the Euclidean plane. It's open somehow. Okay, so now the last step is to prove that the large time behavior of the PDE behaves as we want. So the expected value of the law, which is written here in explicit form, for t large enough will be very, very close to a global minimizer. That's what we would like to prove. And here we use two quantities that are very important for the analysis, is the expected value, and then there is the variance of the law. There are other constants that are appearing. Here there is this constant that is exponential with respect to the difference between the largest value and the smallest value of the objective function over the sphere. And there is another constant that depends on sigma, which is the strength of the Brownian motion, that we would like to take into consideration. Now, there is a very important principle that is called the Laplace principle that tells you that the infimum of a function on the support of a certain measure can be computed as a limit for a temperature parameter going to infinity of -1 over the temperature parameter, the logarithm of the integration over the measure of the exponential of e to the minus alpha times the function you want to minimize. So this is a very important object that tells you that you can compute the infimum by approximating by using this kind of formula. Now, if you combine this formula and the inverse continuity property that I mentioned to you, then in a certain sense, and you substitute to V now the expected value at some time rho t, you can prove that the distance between the expected value and V star has something to do with the value of E at the expected value and the infimum. And the infimum itself can be approximated by using this limit. So for alpha large enough, this infimum will be close to this formula up to an epsilon that you can prescribe. And by using this kind of approximations and massaging a little bit the algebra, you get that basically the distance between the expected value and the global minimizer is dominated and completely controlled by the variance. And so what you're left with is to show that the variance goes to 0, basically, that in a certain sense is vanishing. And for doing that, what you do is you simply differentiate the variance. And okay, it's very complicated, but eventually what you can get after some algebra is that somehow the variance has a coefficient lambda appearing with a negative value, and other coefficients that are appearing with positive sign. okay, with positive sign, and other terms that needs to be determined, okay? The idea will be that we can choose lambda and sigma in such a way that here we gain a negative value so that we have an exponential decay of the variance, right? So the problem is how to deal with these other terms and try to understand. So as you see, this is almost the variance, except this term that you want like to be very small or something like that, or negative. And so no, you want this term to be too small or stuff like that. So or too large. Sorry, you want like that this term is becoming too large. Well, as a matter of fact, if you start with a variance that is not too large, then all these terms appearing here are basically constant. They are basically very close to 1. Okay, so it's so this term is basically not really complicated. A bit more technical is to prove that this term is never too large, and so that you can compensate always with this negative lambda this other term here. And so you can gain the exponential decay of the variance, and with that closing the proof. And as I said, then you can have this kind of triangle type of inequality to obtain that the numerical algorithm, the algorithm really working with a finite number of particles and on a finite number of time steps and so on, converge really to a global minimizer. Okay, so this is more or less the architecture and how the proof is spelled out with some details. Now we can come to some applications to try to compare this algorithm with respect to some state-of-the-art algorithms for a certain kind of problems. One problem that we can consider is, for instance, phase retrieval. So you can consider here the measuring of a certain vector z star by using the scalar product with respect to other vectors, of which we consider the magnitude square plus possibly some noise. And the problem is reconstructing z despite the fact that we lost sign information or phase information from these scalar products. This problem is well known, especially in this community. Many people have already seen it. And one way to solve it is by minimizing simply the empirical risk, which means that you try to minimize the discrepancy between the left and the right side. And in particular, it's possible to prove that you can reformulate this problem as soon as the lower bound of AI as a frame is known. It's possible to rewrite this problem completely on the sphere. And because of that, somehow you can solve the original problem by solving the corresponding version on the sphere. This is a quartic type of function, and so it's clearly non-convex, let's say, and it's clearly potentially a difficult problem. And so if you compare this algorithm with a state-of-the-art algorithm like vertical flow and other algorithms that have been designed ad hoc for this method, and typically methods that use gradient information, because vertical flow, for instance, is a gradient flow. So it's basically considering a gradient descent with respect to this cost. You can see that our algorithm that we call Kuramoto-Wischek basically has a phase transition diagram in the sense of the number of frame vectors that you use and the ability of reconstructing the vector z star that is not as efficient, as good as the vertical flow, but is as good as other algorithms that have been designed ad hoc for this method or for this problem. While if you compare it to signal to noise ratio, you can see that as soon as you have enough vectors for the reconstruction, the robustness of the method is as good as vertical flow. Another example is about the robust linear regression. So if we have a bunch of points in our M, and they characterize a certain kind of data, and we want to find the best fitting one-dimensional linear subspace through these points, and we want to design this problem in such a way that if there are outliers, their weight in understanding the distance of the points from the one-dimensional subspace is made in a certain sense favoring those points that are closer to subspace rather than those far away. One can formulate the problem as minimizing this cost function where the exponent p is a small exponent, typically an exponent less than 1. In such a case, this function become highly non-convex with a lot of local minimizers that basically they represent local clusters of these kind of points, and so it becomes very sensitive to these local clusters, and so you have a lot of local minimizers. So this function won't be easily minimized as it were for the phase retrieval by using a gradient descent, and so this is a definitely more challenging type of problem, and we tested it on somehow comparing it with other methods that are somehow based on sort of iterative reweighted least square of this kind of problem proposed by Lerman and others. And this is a sort of ad hoc method that is almost a quasi-Newton method, so it's not really computing a gradient, but still it's a higher order type of methods rather than simply evaluating the zero order type of information, right? So here we consider either a set of points that are faces or faces with outliers. And in the case of, say, faces with no outliers, and we can compare somehow the choice, the minimization of this with p equal to 2 with a singular value decomposition, and you can see that somehow the first singular vector is exactly reconstructed. In the case where somehow we do have outliers, the singular value decomposition won't be as clean as the other in the other situations, while optimizing this function with p less than 1 by using our method somehow allows you to, in a certain sense, being able to be more robust with respect to outliers. Okay, this is a proof of concepts also of the usability of this method in high dimension, because these images are all of 2,880 dimensions. So these are vectors in 2,880 dimensions. So the algorithm can be used and scale well in such a dimension. And you can ask yourself, how many particles do you really need? Well, here we used a very, very large amount of particles to solve the problem, but nevertheless, it's possible to formulate, and we have nearly done it, versions of this method that instead of having an isotropic Brownian motion, they do have a sort of anisotropic Brownian motion. And in this case, we could solve this problem with a number of particles that does not exceed 500. And so in a certain sense, we can have results that are pretty scalable with the dimensionality and so on. So with this, I would like to thank you for your attention, and I remain at your disposal for questions if you have any.
Thanks a lot, Massimo, for the interesting talk. I think we open the floor for questions. So feel free to just unmute yourself and ask.
Hi, Massimo. I have a couple of quick questions about the main theorem.
Yes.
So I was wondering about the implicit dependence on dimension, where it sits and what it looks like.
Okay. The only place where we are a bit concerned about dimensionality is essentially this constant here. So we think that it could be that alpha needs to scale with the dimensionality, okay? And this constant appears also here in this formula. I did not make it explicit, but this could be a place where the dimensionality might play a role. But we don't observe the curse of dimensionality. So we don't see that you need an exponential number of particles to do the job. And in many of these examples, as I said, we have been playing with high dimensionality, so d equal to nearly 3000. If there were curse of dimensionality, you would need to use zillions of particles, but that's not the case. I mean, you can do the job with 500. And so on the one side, we have empirical experience that there is no curse of dimensionality, and we have no theoretical confirmation that the theory that we have. So there might be some issues about this constant, but I'm not sure about that. Okay, certainly we were able to avoid that this scales like n to the -2 divided by d. That was something that we were fearing quite a lot.
Great. And maybe like also about sensitivity to parameters,
Yes.
how randomness shows up. I mean, the Brownian motion, if it's not random enough, it would take probably too long. And if it's too random, then maybe you miss important things. So does this appear, or?
Yes. First of all, somehow the calibration of the parameters, it's with as many algorithms, you know, that requires a little bit of tuning, right? So as I said, the natural rule of thumb that the theory gives you is pretty respected. So you really need somehow this kind of scaling. As I said, in this scaling, there is some dependency on the dimension, right? And so, in a certain sense, the Brownian motion become less and less strong in higher dimension because this constant has to be bounded by your lambda, and this plays a role. But in the anisotropic case, so that we have not yet submitted, but we are almost finishing, we have a method that is where the dependency on the dimension in the parameters is dimension free. The dependency is dimension free. So the tuning of the parameters can be hard work. I think that is a matter of experience, gaining experience with different problems, and being really able to tune the parameters. But we have experience now also with an isotropic case that if you use a generic type of parameters, the method may not work. So if you just generate the parameters at random and then you run the algorithm, it may not work. But if you include from time to time picking one particle, one single gradient descent step. So out of the many particles, you elect one particle every, say, 10 iterations, and this particle you make it going down with a gradient descent. All of a sudden, the random parameters setting for the algorithms are enough to make it converging. So in a certain sense, there are some weird tuning that you can do to make the algorithm less parameter dependent. Yeah.